So today we will continue from where we stopped yesterday. Gauss law in electrostatics. Many of them told me this answer also. You've learned this already. Total electric flux through any closed surface will be equal to 1 divided by epsilon naught times the total charge enclosed by the surface. So this is Gauss law in electrostatics. As we move on to further topics, we also have one more law called as the same Gauss law, but that is Gauss law in magnetism. So when you answer your questions for the exam, you should keep in mind whether they are asking us questions related to Gauss law in electrostatics or Gauss law in magnetism. So this law, what is shown for you, is Gauss law in electrostatics. That is, total electric flux through any closed surface will be equal to 1 divided by epsilon naught times the total charge enclosed by the surface. Now, knowing this, we will move on to our next derivation. You have to derive an expression for electric field at a point due to infinitely long straight charged wire. So keep in mind, we are going to use Gauss law and we will derive an expression for electric field at a point due to a straight charged wire. And you know, wire will be a conductor. So your question can also be derive expression for electric field at a point due to a conductor. Then also the same derivation should follow. So we are doing it for a charged wire. And what are the properties of the wire? It has to be infinitely long and it has to be a straight charged wire. Now you have a diagram here. This is an expanded diagram of a wire. You know what will be the thickness of the wire. So the same thing is enlarged so that we will be able to understand. See, we have two surfaces for this wire. One is A, the other one is B. So two ends are denoted by A and B. The length of the wire is denoted with the symbol L. And you have one force acting perpendicular to the wire that is denoted by the symbol N. You can see the arrow mark upward as well as in the downward. This is the perpendicular force. N denotes your normal force. And at the points or at the surface A and B, there are two more forces acting. One is electric field upward and N is the normal force which is acting in the horizontal direction. The same way for this side also. You have E in the upward direction and N in the horizontal direction. And you can see charges, positive charges are arranged across a line. That center line is called as the axis of the conductor. So this is our diagram. We'll draw one wire, label the two ends as A and B. And on the both the surfaces, you'll draw E vertical line, N will be the horizontal line, N cap is your unit vector. Then through the center, one perpendicular line you will draw, N cap, N vector, and here you have E that denotes your electric field. And the radius of the wire is L. The length of the wire will be denoted with the symbol capital L. So these are the diagrams which you have to draw. Now after completing your diagram, we'll see our derivation. The electric flux through the two end faces, that is A and B, to the end faces will be 0 because ds vector, ds is the surface area vector, and E, that is your electric field, are perpendicular to each other. So when they are perpendicular to each other, angle will be 90 degrees. And you know very well, cos 90 is 0. Cos 0 is 1 and cos 90 is 0. So on both the surfaces or both the ends, the electric flux will be 0 at the end A as well as at the end B. Reason, ds vector, the surface vector, and electric field are perpendicular to each other. So theta becomes 90, cos 90 is 0. So these 2 points are not considered now, A and B. You can see your point C here. So this flux will be given by the formula pi equals, the symbol is for pi, E ds into cos theta. So when you take E ds, It is the electric field multiplied by your area, which is ds, and cos theta. This is the general formula what we have. Now if theta equals 0 degrees, you can see the line here between E and N, it is perpendicular, or both are in the same direction. Both are moving along the horizontal direction. So for the point C, when we take the electric flux, can you see any angle here? It's both the lines are on the same line. So your theta value will be equal to 0. So substitute 0 here. Pi equals E ds into cos 0. Cos 0 is 1. Therefore, pi will be equal to E into ds. I'm repeating it. For these two surfaces A and B, for the end of the wire, your flux will be equal to 0 because ds and E are perpendicular. Cos 90 becomes 0. When we take the third surface, that is a lateral surface or the horizontal surface, for the point C, angle between E and N or E and ds vector between the area will be 0. Cos 0 is 1. So our formula will become pi equals E into ds into cos 0. Since cos 0 is 1, pi will be equal to E into ds. ds, I told you, it is the total surface area. If you recall your mathematics, we have formulas for surface area of a cylinder. So surface area of a cylinder is nothing but 2 pi r into L. This is the basic general formula what we have. So for a cylinder, the surface area ds is equal to 2 pi r into L. So in place of ds, just substitute 2 pi r into L and call this as equation 1. By Gauss theorem, what is our theorem? The total flux is equal to 1 divided by epsilon naught times your total charge. So mathematically, pi equals 1 by epsilon naught into Q. Q will be the charge here. For the charge on a cylinder, your formula will be Q equals lambda into L. So pi equals 1 divided by epsilon naught. In place of lambda, you can write it as, in place of Q, you can write it as lambda into L. Call this as equation 2. Now when you compare equation 1 and 2, your right hand sides are equal as pi and pi. Equate your left hand sides. E into 2 pi RL will be equal to 1 divided by epsilon naught into pi into L. What will cancel here? You just observe both the equations are equated now. You can cancel out L and L on both the sides. So this will become E is equal to lambda will be there in the numerator. All the other terms will come down to the denominator. That is 2 pi epsilon naught into R. So this is the expression we need in case of a cylindrical wire or a charged wire. This is a 5-mark question. Using Gauss theorem, derive an expression for electric field at a point due to infinitely long straight charged wire. Very fast, we will revise it again. Point number 1. Electric flux through the two ends will be 0 because ds and E are perpendicular. Theta equals 90 degrees. Cos 90 is 0. Point number 2. Electric flux at the point C is given by the formula pi equals E ds into cos theta. Here, theta is equal to 0 degree, cos 0 equals 1. Therefore, pi will be equal to E into ds. ds is the surface area of a cylinder, which is equal to 2 pi r into L. So substitute that. Pi will be equal to E into 2 pi RL. Call that as equation 1. Third point, by Gauss theorem, total flux is 1 by epsilon naught times the total charge. Mathematically, pi equals 1 divided by epsilon naught into Q. Q will be equal to lambda into L. Hence, pi equals 1 divided by epsilon naught into lambda into L. Call that as equation 2. Equating equation 1 and equation 2, E into 2 pi RL will be equal to 1 by epsilon naught into lambda L. L and L will cancel up on both the sides. Then you will get E is equal to lambda divided by 2 pi epsilon naught into R. So this is our required expression for electric field. Now the same derivation, we will do it for the next. We are going to derive an expression for electric field due to a uniformly charged spherical shell. So what first we did for a wire. Now we are going to do it for a uniformly charged spherical shell. Just observe it.